Welcome back to the final section today. I'll be talking about time-lapse monitoring of subsurface velocity changes across Utah and some neighboring states. Before I start my talk, I would like to remind us a result that we saw last year from one of our fellow CWP students, Nuri. Well, actually, he's a doc now. So what they did in their study was to monitor near-surface velocity changes, annual velocity changes across the whole of Japan for a number of years. And also they did the study before and after a major earthquake in Japan, the Tohoku earthquake, which occurred in 2011. And from what they saw from their results was that there were significant velocity changes, annual velocity changes across the whole of Japan. But they actually saw larger velocity changes in the near surface due to stress changes resulting from the earthquake event. In their study, they were able to make a connection of these velocity changes to changes in precipitation, which were explaining the annual velocity changes and also the stress changes due to the earthquake event. But for our study, we're not investigating Japan. We're investigating somewhere within the western part of the United States. This section of the United States is well known as a highly deformed section of the US, characterized by various tectonic behaviors. This includes series of faulting and extensions. This is shown by this figure with where you see the red arrows show extensive extension stress, while the blue arrows show compressive stress. The shaded region in our figure Y is just a reference point which depicts the Yellowstone. But for our study, we are focusing on a smaller region in this outlined by, defined by the outline section. This section covers a part of, as I said earlier on, Utah and some neighboring states. But there are two major features within this region, which is a major fault that occurs across Utah, Washout Fault, and also towards the north, you have the Snake River Plain. Our goal in this study is to investigate for velocity changes over a period of time. I want to answer this major question. Are there like subsurface velocity changes within the subsurface covered by this region? If we see any velocity changes, how large are these velocity changes? How frequent are they occurring? And where within our monitored region are these velocity changes seen? To answer this question, we use data sets generated by explosive signals shown in this figure. These are explosions that were conducted by the military army in Utah in 2007 from June 4th to September 10th. So we have 10 of these explosions spaced out within a week or two. The interesting and peculiar thing about this data set is that the source characteristics and the source location of our signal is very similar, such that the differences we see in our signal can be attributed to the differences within the subsurface throughout the time-lapse period we are monitoring. And these explosive signals were recorded in the USArray given in this figure. These are nearly regularly spaced receivers depicted by the square the white squares. The red star gives you the location of the source. The regular space array helps us to describe especially the spatial variations in the velocity change we might observe. So using the data set, we adopted a certain data processing scheme. Part of the data processing involves using 1 to 5 hertz bandwidth of our recorded explosive signal. We use the Coda section of our the waveforms, and to estimate the velocity change, we use an algorithm which is a stretching algorithm. We're a little bit on the detailed on the data processing. This is the typical signal that was recorded from the explosive signal, showing the three different components we are working with. The dominant signal is the explosive signal. But alongside with this explosive signal is long wavelength waveforms recorded in our station, and also significant noise that is present that was also recorded in the signal. Using 1 to 5 bandwidth of the waveform, we're able to remove substantially the noise present in the signal, and also the long wavelength part of the waveform. And also we use because our focus is to monitor velocity changes, and we want to increase the sensitivity of our the sensitivity of the velocity change we estimate, where we use only the Coda section of the waveform. And this is the part of the waveform that we believe that have resolved from multiple scattering of the explosive signal that traveled through the subsurface before they were recorded in our receivers. This part of the waveform is depicted by the exponential decay in the amplitude after the direct arrivals. In this case, where we limit ourselves to the S-wave coda. As I said earlier, using this part of the waveform, we will increase the sensitivity of the velocity change we monitor. A lot of studies have shown that using this sort of waveform, we are able to estimate velocity changes in the order of 0.1%. So to estimate the velocity change, we use the stretching algorithm. This is similar to some of the algorithm, dynamic time warping algorithms, but in this case, we'll simplify it by making an assumption that our shifts are linear, so that the stretching is controlled by epsilon, which we'll call the stretching factor. This stretching factor is equal to the average fractional velocity change that is present in our time-lapse signal. Using this to estimate the optimal velocity change that is present in our time-lapse signal, we used an L2 norm objective function, which minimizes the misfit between a baseline signal and the time-lapse signal, the time-lapse signals. And you expect that the optimal stretch factor occurs at the minimum objective function. Using this data processing scheme, we estimate the velocity changes for all the period of time we're monitoring, and for all our monitoring stations. Here is a result showing velocity changes estimated for all the stations, the average value for all the stations for each period, each time period we are monitoring. From this, these estimations were made for all the three components independently, as you see in the results. And for each of the three components, we see similarity in the variations in the average velocity change. But the interesting thing in this result is that the magnitude of the velocity change we're able to resolve. This allows us to estimate velocity changes as low as less than 0.1%. But you might ask me a question that, given the error values you are seeing in this figure, are these trends in the velocity changes realistic? I'll shed more light on the magnitude of this error in the next slide. But if you look at the estimated velocity changes as against the source receiver distance for each station, you see a relationship of the estimated velocity change for with the source receiver distance for each station. And this relation, there seems to be like a decrease in the estimated velocity change for each station as we move away from the source location. This is because of this is associated to the sensitivity that you encounter, which tend to decrease when your source receiver distance increases. So for us, and this explains the reason for the large error we saw earlier on, because those were computed by just computing the standard deviation of this estimated velocity change. For us to be able to characterize those errors very well, we need to understand this behavior better. This also leads us to a very important question. Given this decrease in sensitivity as you move away from your source location, how much are these estimated velocity changes a representation of the localized velocity change within the subsurface, so that the in situ velocity change that is present within the subsurface? We can answer this question by with this expression, which relates the estimated velocity changes for each station to the in situ velocity change given by delta V over V. This relationship is defined by what we call the sensitivity kernel K, which depends on your source location and also your receiver location. For a 3D half space, the expression of the sensitivity kernel can be given as follows, which, as I said earlier on, depends on your source and receiver location. In this case, you have the big R is the distance between your source and receiver, while small r and small s are distances of an arbitrary location within the subsurface from either your receiver or your source location. But the sensitivity kernel depends on a parameter that is called D, which is called the diffusion coefficient. The sensitivity kernel of this expression is derived by assuming that our Coda wave, which is a multiple scattered wave, results as can be described as a diffusive process, such that the characteristics of the multiple scattered wave is defined by this coefficient, and the diffusion coefficient is a property of the heterogeneous subsurface. Using this coefficient, we can now infer for the in situ or the localized fractional velocity change, the delta V over V we saw earlier. But for us to infer for that for our data, we made a simplifying assumption that the velocity changes we are observing observing from our monitored stations results from a velocity change within the subsurface that extends to the monitoring surface. And we have make another assumption that this velocity change is uniform across within the subsurface, so that the amount of the velocity change now is defined by the magnitude of the velocity change, delta V, and also the depth extent of the velocity change given by Hedge. Using this assumption, we can simplify the equation that relates the estimated velocity change to the localized velocity change to this simple relationship, which will shows explicitly how the estimated velocity change depends on the source receiver distance, the big R. Well, this relationship is connected by a series of coefficients, C, which is just an integral, which is a factor that just depends on the geometry of the problem we're working with. but it also depends on some other parameters, the edge, which defines the depth extent of the velocity change, and also the magnitude of the fractional velocity change present in the subsurface. But with this expression, we only limited to the resolution of the combined parameter of edge and delta V over V, because with our data set, we can only resolve this combined parameter. There's a trade-off between the volume of the velocity change, in this case defined by edge, because we are making an assumption that the velocity change we're monitoring is uniform across the subsurface. There's a trade-off between the volume and the magnitude of the velocity change. With this relationship, we can now describe the spatial distribution of the velocity change we saw earlier on by this is an example of the field for the velocity changes estimated for a particular time period across our receiver array. And what they say is that the fit is done independently for all the different components, the two horizontal and the vertical components. And for all the different components, we get a similar fit for the spatial distribution of the estimated velocity change. Using those fits, as I talked earlier on, we can only estimate the delta, the combined parameter of edge and delta V over V. Here is the estimate that we get from the fit of the spatial distribution of the velocity change. And this gives you the similar trend we saw earlier on by just averaging the velocity change. But the good thing about this is it allows us, because of we have a better understanding of how the velocity changes vary with distance. We now have a better description of the error associated to these estimated velocity changes. But the flip side to that is that we cannot now extract just the magnitude of the velocity change, but we only have a control on these two parameters, which is the volume of the change and the magnitude of the velocity change. Something I didn't mention when defining the sensitivity kernel is the impact of major discontinuities within the subsurface. And I forgot earlier on to say that, point out that our monitored region covers a huge extent, which covers over a region of hundreds of kilometers. This leads to a major question: how major discontinuities within the subsurface affect your estimation of the sensitivity kernel. And one of the major discontinuity within the subsurface is the cross-mantle discontinuity, known as the moho. The moho lies about 25 kilometers within our monitored region from the surface, from the free surface. What that does is that it tends to make rather than our monitored region being an infinite space, can be considered as a thin layer. If you include the moho in the computation of the sensitivity kernel, we get this sensitivity kernel result, which here is this a plot of the sensitivity kernel perpendicular to a particular source receiver line at the middle of the source receiver line. If you compare this to the sensitivity kernel compute from just removing the moho and assuming a 3D house space, that is what you get. And what you see from the result is that there's increase in the sensitivity kernel with the presence of the moho. This is because like most of the scattered waves that we are recording can be seen as to be can be assumed to be limited just within the tiny slab, tiny crustal slab. The impact of this is that if you use to invert for the combined parameter of H and V, the increased value in the K value will now reduce the magnitude of the inverted combined H and delta V over V. Another aspect of this study is to not just estimating these velocity changes, but is saying something about the causes of these velocity changes. This is an ongoing research work where we've been looking at trying to make a connection between the estimated 4D signatures we see in our data to some of the possible causes. And some of the leading candidates include changes in groundwater within our monitored area time period. Here in this result, it's comparing the estimated inverted combined H delta V parameter to cumulative groundwater subsidence from a particular well within our monitored region. And what you see from the independent data is that there seems the variations of these two information shows strong relationship between one another, which with an initial increase, then I think we'll later on have a decrease in the two data sets. So groundwater subsidence might explain the velocity changes we are observing from our monitored region. But I would like to point out that this groundwater subsidence is just occurs within a very thin layer. This is a subsidence of just few meters. What this means is that if I assume that just the changes occurring within a very thin layer in the order of few meters, our delta V over V might we expect to estimate from these values will now be about 50%. And this seems really unrealistic for Utah, especially during the summer, where we witness limited precipitation. Another explanation might be broader crustal deformation that we know that's present within our monitored region. Here is showing deformation rates, long-term deformation rate and short-term deformation rate. These are deformation rates that were filtered within for a period of a year and half a year. And what you see from these variations in the deformation rates is the deformation rates show significant variations, even both for the long-term period and the short-term period. And the interesting thing about this variation is that with this sort of variations, you expect velocity changes that occur over a deeper section of the cross, though in a more gradual than what you expect for the groundwater change effect from the groundwater changes. And with these changes, for our estimated combined parameter of H and delta V over V, we now expect our delta V over V to be in the order of 1%, which is more realistic for the Utah. So in a summary, I would like to say that from our study, we are observing significant velocity changes across the subsurface within Utah and some of the neighboring states. The method we are using here allows us to estimate very weak velocity changes as small as 0.1%. But in our study, we are still making the connection between the estimated velocity changes to the causes of these velocity changes. And for now, we don't have a definite answer, but the velocity changes might be as a result of broader crustal deformation within the area or changes in the groundwater level across our monitored region. At this point, I'd like to thank the Department of Energy for sponsoring this project and welcome your questions.